Hi, good morning. Last class we have discussed about closure operator and some examples. Now also we are continuing the same procedure. Now the operator AX equal to dx by dt in L201 with the domain equal to set of all x belongs to C01 with x dash belongs to C01 x0 equal to 0 is not closed but admits a closure. Its closure is the operator defined in the previous example. We have discussed this in our previous example. Okay. Now consider another operator A from L201 to L201 defined by Ax equal to x0 into t with and domain A equal to this one. This operator does not admit a closure. Okay, just recall the definition of a admits a closure. Now, if you take x and t equal to this one, x and t equal to 1 minus nt, 0 less than or equal to t less than or equal to 1 by n, 0 if 1 by n less than or equal to t less than or equal to 1. Then what happens? We get a x and t is equal to t, but x and t tends to 0 in L201. We have xn0 equal to xn0 equal to 1, ax and t equal to, by definition, ax equal to x0 into t. So axn equal to xn0 into t. Xn0 is 1, therefore t. Therefore we get ax and t equal to t. Okay. Thus we get this ax and t equal to t. Now axn, where is axn? Ax and t equal to t. This is same as I of t. So axn is converges to an identity function. Okay. Now what is norm of xn square? We have xn is like this. Norm of xn square is equal to integral 0 to 1 by n norm of 1 minus nt. This is the space L2. L2 is second integrable function. Therefore, norm is this one, integral 0 to 1 by n minus t whole square dt, and that's equal to integral 0 to 1 by n 1 minus 2nt plus, okay, this one. And if we integrate this and applying limit, what we get is this is equal to 1 by 3 by 3n, and that tends to 0 as n tends to infinity. So xn tends to 0 function. Okay. Therefore, this operator does not admit the closure. Now next is very important theorem. This is called closed graph theorem. Okay, Banach. And this theorem is called closed graph theorem. Now what is a closed graph theorem? Statement you must clear. Okay. Let x and y be Banach spaces and let a from x to y be a closed graph operator and domain of a equal to x, then a is continuous. That is, a is a bounded operator. Okay, let x and y be Banach space and a from x to y be a closed graph operator and a domain of a equal to x. Then a is continuous, bounded, or a is a bounded operator. Now let dy be a unit ball in y centered at 0. Let dy be a unit ball in y centered at 0. We have to prove that A inverse dy is perfectly convex. Okay. So for this, take a bounded sequence xi in A inverse dy, and we have to prove that sigma alpha xi belongs to A inverse di. Okay. So xi belongs to A inverse di means what we get, axi belongs to dy. And let yi be axi. So yi belongs to dy. Dy is an open ball. Every open ball is perfectly convex. Okay. So let alpha I greater than or equal to 0 be such that sigma alpha I equal to 1. Then the series sigma alpha is absolutely summable since xi's are bounded, because xi belongs to xi is a bounded sequence. We already assumed that xi is a bounded sequence. Now what about how we prove sigma alpha is a boundedly summable, absolutely summable? Sigma of norm of alpha xi equal to This you can write as alpha is are greater than 0. This is same as sigma alpha I norm of xi, and bounded means norm of xi less than or equal to k, and this is equal to sigma alpha I k, and this is equal to k into sigma alpha I, but sigma alpha I is 1 k. Since X is a bounded sequence, every absolutely convergent series is convergent. So, sigma alpha is also convergent. Let X is equal to sigma alpha I xi. Similarly, since Ya is a bounded sequence and Y is a Banach space, we get sigma alpha I Ya is convergent. Okay, but we know that as dy is an open ball, dy is perfectly convex. Sigma alpha I Ya belongs to dy. Okay, since A is a closed graph operator, we get Ax equal to Y. Okay, because by the definition of closed graph operator, okay, we get Ax equal to Y. This implies X belongs to dy. That is what is X? X is sigma alpha I xi. X is sigma alpha xi implies sigma alpha xi belongs to A inverse dy. So, if you take any bounded sequence xi, then sigma alpha xi belongs to A inverse dy. This implies A inverse dy is perfectly convex. Now, since domain of A equal to X, we get 0 belongs to kernel of A inverse dy. But kernel of A inverse dy is same as interior of A inverse dy. Therefore, from this we get 0 belongs to interior point of A inverse dy. That implies A is continuous. Okay. Now there is a remark. It is possible to prove closed graph theorem from the open mapping theorem with the following argument. Consider the subspace E equal to set of all ordered pair xy such that y equal to ax. And clearly this is a subset of x cross x cross y. If A has its graph closed, then E is this is a graph, okay. Then E is a closed subspace of a complete space x cross y, because x and y are Banach space, okay. X cross y. So, E is a closed subspace of a complete space x cross y. Therefore, E is complete. Okay. Now define u from e to x by u of xy equal to x. Then the operator u is bounded. How we can prove this? Norm of u of xy is equal to, what is by definition norm of uxy is norm of x, and this is less than or equal to norm of x plus y, and this is equal to norm of ordered pair xy. Therefore, norm of uxy is less than or equal to norm of xy. This implies u is bounded. And since domain of A equal to X, it is onto. Also, the operator is 1, 1. How we can prove? You takes two elements, u x1, a x1, x2, and this implies x1 equal to x2, because by definition u of x1, a x1 is x1, u x2, x2 is x2. So, this x1 x equal to x2 implies a x1 equal to x2. Therefore, this ordered pair is C. Therefore, this operator is 1 to 1. So, U is bounded onto, and 1 to 1 implies U inverse is also bounded. Now, if you define the operator T from E to Y defined by T of xy equal to Y, and it is also continuous, then thus A equal to T U inverse. T is also continuous operator, U inverse bounded, therefore T U inverse is also a continuous operator. Now what is a T U inverse? T is a bounded operator, U inverse bounded implies both T U inverse is bounded operator. Now what is T U inverse of x? T U inverse of x is U inverse U of x ax is x is. So T U inverse of x means T of x ax. Now T of x ax means ax, because we assumed T x y as y. So ax for all x belongs to. So T U inverse is equal to A. So U inverse and T are continuous implies A is also continuous. Okay, that's all for today's class.